We talked briefly the other day when we were talking about these types of forces, about what we call a free body diagram, sometimes abbreviated by FBD. Free body diagram is a diagram that shows all of the forces acting on an object. Okay, we touched on it the other day because we were touching upon different types of forces that we may have to include in a free body diagram. But in the end, we didn't really say why we needed to do it. Okay, today we're going to see why we need to do it. We're going to learn that reason. Okay, we need to draw a free body diagram whenever we have more than one force acting on the object so that we can analyze those multi-force problems. We're going to draw a couple free body diagrams, and then we're going to look at a couple multi-force problems, and you're going to see how it's a useful tool in solving those problems. Here's our first problem here. This is just a free body diagram problem. It says, it's chapter 3, by the way, page 131. It says, a car with a weight, which is a force of gravity, of 10,000 newtons downwards is coasting on a level road. The car experiences a normal force of 10,000 newtons up, right? We saw that when we were dealing with friction yesterday. Every single time we dealt with friction, the normal force was equal to gravity. So here you see it's 10,000 up for normal force, 10,000 down for gravity. Now that's not always the case. I told you I'd teach you later on when the normal force is not equal to gravity. Right now we don't need to worry about that. There's also a force of air resistance of 2,500 newtons backwards and a force of friction exerted by the road on the tires of 500 newtons backwards. Draw this free body diagram. So here's the car. It's a rather ugly car. It's rather boxy. We have, what, 4 forces acting on it? We have a force of gravity acting down of 10,000 newtons. And we have a normal force acting up. We're going to draw the normal force the same length as we draw the force of gravity because it's the same value. They're both 10,000 newtons. Now, it's important that we draw them both the same length, and it's also important that we draw them both in the right direction. What's not important is where I draw them. I drew the normal force right there underneath the car, pushing it up. I could have just as easily drawn the normal force right here, as long as I drew it the right length and in the right direction. It doesn't matter where you put it, it just matters how big you make it and what direction it's going. So those are both correct, okay, but I could have easily drawn it like this and like this, or I could have drawn it like this and like this, or whatever. Now we get 2 more forces acting here. We have a force of air resistance that's acting backwards. It's 2,500 newtons. So I'm going to try to draw that shorter. It's about 1/4 the length of the normal force and the force of gravity. I don't expect it to be perfect with the length of it. I just want to see that you recognize that it's a smaller force than gravity and the normal force. So it's a shorter vector. Finally, we have a force of friction by the road on the tires. It's also 500 newtons backwards. I'm kind of running out of space over here on the left-hand side, so I'm going to draw that force of friction like this. Now, it seems like maybe that force of friction should be drawn over here, right? But remember what I said a minute ago. It doesn't matter where you draw it. What matters is that you draw in the right direction, and I've got it drawn to the left, backwards. And it also matters that you draw it roughly the right magnitude. And clearly you can see here that my 500 newtons is shorter than my 2,500 newtons and quite a bit shorter than my 10,000 newtons. There we go. There's my free body diagram for this car that's coasting on this level road. If it wasn't coasting, if the engine was applying a force, well, then there would be a force to the right. Maybe we call it an applied force or the force of the engine. But since it's coasting, that's not there. All you got is air resistance, friction, normal force, and gravity. You'll see shortly how this becomes, again, really useful in solving problems. Right now, it seems like kind of just an exercise in, almost make work. Like, hey, here's some work for you to do. Draw all the forces acting on this object. But it does become really useful. Okay, I promise it does become really useful when we're solving problems. I'm going to get you to draw a couple free body diagrams yourself first before we work on some of those problems. Page 131, please. Let's do question 2. It says a car moving at a constant velocity starts to speed up. The weight of the car is 12,000 newtons down. That's the force of gravity acting down. The force of air resistance is 3,600 newtons backwards. And with the engine engaged, the force of friction exerted by the road on the tires is 7,200 newtons forward. Wait, that doesn't make sense, does it? How can there be a force of friction opposite to air resistance? If I'm moving one way, air resistance is pushing me back. How can friction be pushing me forward? That's how cars move, right? That's how cars move, is a force of friction between the tires and the ground pushing it forward. You apply a force on the road applies a force back on you. All right, let's draw the picture of that now. Here's my car. When you're drawing these diagrams, it doesn't have to be pretty. You don't even have to draw wheels on your car. Draw it as a box. I don't care. Okay, it's not the car that's important here. It's the forces acting on it that's important. What do we got here? We have a force of gravity acting downward. That's 12,000 newtons. I don't care whether you draw that where I have it drawn or whether you have it drawn right here, as long as you have it drawn downwards. My force of gravity, 12,000 newtons, and I have it drawn downwards. I've got a force of air resistance backwards of 3,600 newtons. I'm going to draw it about like this. Backwards, 3,600 newtons. With the engine engaged, there's a force of friction forwards. It's going to be bigger than air resistance, but smaller than gravity. That's it, right? Is that it, Riley? Yeah, it doesn't say anything about the normal force, but if you got a car on the road, there's got to be a normal force, right? That normal force is going to push which way? Up, 90 degrees to the ground, right? And how big is it going to be? Assuming the car is not on a hill, or assuming the car is not accelerating up or down, it's going to be the same as gravity. So I'm going to draw it right here, same length as gravity, and I'm going to say the normal force is the same value as gravity, 12,000 newtons. All right? All right. So what do we do with this now? Okay, what use is this tool for us in our toolbox? We're going to use it when we're analyzing what I call multi-force problems. A multi-force problem is a problem where we want to maybe find the acceleration or find something mathematically that has more than one force acting on it. The strategy starts off with drawing a free body diagram, always, and then canceling out any forces that you can. Let's go back to this one for a second. Are there any forces that I could cancel out there? In other words, any forces that balance each other? Taylor? Yeah, gravity and the normal force, right? You want to cancel out any forces that are the same, any forces that balance out each other. That makes life a little bit easier when you're going to solve this problem mathematically, because we only have 2 forces instead of 4 forces, and because we're dealing now only with the x-axis instead of with the x and the y. Does that make sense? Imagine what would happen if we couldn't cancel those out. We'd have forces this way and forces this way. It would become a 2-dimensional problem, an x component and a y component. As it stands right now, because they cancel, all I've got is the x, a horizontal problem. Let's go back to this one. Any forces I can cancel out here? Once again, gravity and normal force. For a lot of these problems, that's going to be the case. Gravity and the normal force will cancel out. Occasionally, you might have a force forward and a force backward that will cancel out as well, but usually it's gravity and the normal force. Get rid of whatever you can to simplify it. Draw your free body diagram, scratch out or cross off anything you can. Now, if all of the forces that are left are in one dimension, which they are in the problems that we did, then I want you to do the following. If they're not, if you got a force like this and a force like this and a force like this that's left over, this doesn't work. Okay, that comes later on for us. If they're all in one dimension, however, you're going to do this. You're going to say F net is equal to all of the forces that you have left. If you have 2 forces left, then we'd say F net is equal to F1 plus F2. If you have 14 forces left that haven't canceled out, then it would be F1 plus F2 plus F3 plus so on. Remember that F net is the total unbalanced force. So we're going to say F net is equal to the total of all the forces. Make them all positive. Just leave it all positive here. We'll worry about direction later on. Now, sometimes, not always, but sometimes you'll sub in M times A for the net force. How come? Well, because sometimes you've either got the value of the acceleration or you're looking for the value of the acceleration. You always do this, and you sometimes do this, depending upon the context of the question. And then you plug in numbers and you solve for something. You get what you can get out of this, okay? It's kind of like projectile motion. We don't have to have too much of a strategy. We know where to start, and then we plug in numbers and we get something. Here's an example. Two people, A and B, are dragging a canoe out of a lake onto a beach using light ropes. Each person applies a force of 60 newtons on the rope. There's a force of friction exerted by the beach on the canoe of 85 newtons backwards. Starting with a free body diagram, calculate the net force on the canoe. So if this is the canoe, I know it's not a very good looking canoe, but if this is the canoe, we would have, well, first of all, we'd have a normal force and a force of gravity acting on that canoe. We don't actually know what the value of those forces are, so we can't draw them to any particular length, but we do know that they're equal to each other, so we can draw them the same length. We know that we have a force acting to the right. We'll call it F1, 60 newtons. We know we have another force acting to the right. We'll call it F2 of 60 newtons. And we know we have a force of friction exerted backwards of 85 newtons. So it's going to be a little bit bigger than the 60 newton force. Remember, step one was draw your free body diagram. Step two, get rid of all the forces that you can get rid of. Anything I can get rid of here? Anything that I can cross off because they balance each other out? Yep. Gravity and the normal force. That's a good thing because it would make it a two-dimensional problem and because we don't know what their values are. Can I get rid of the 60s? They're equal. Can I get rid of the 60s? No, because they're not opposite, right? So we got to leave those. Now the next step, we're going to say F net is equal to the sum of all those forces. We would say FF plus F1 plus F2, all of those forces that I haven't got rid of. FF is 85 plus 60 plus 60. Is that right? Yes. When we add them up here, we're just going to call them all positive because we're finding the sum of all the forces. But when we're adding them up with numbers, we have to take into account direction. Negative 85 plus 60 is going to give me, I think, 35 newtons. The net force acting on that canoe is 35 newtons. All right, your homework for tonight is going to be the two questions on page 132, in addition to the questions that you haven't finished up on page 190. So page 190, number 1 to 6 and 10, if you haven't finished those, and page 132, questions 1 and 2.